Hello everyone, this is Introduction to Optimal and Model Predictive Control. This is additional set of notes that is associated without class, graduate class. And today I'm just going to introduce optimal control and later on modern predictive control. Let me start with the first and simple notion about optimal control, which is given as a linear quadratic regulator, and we will consider this on the infinite time horizon. In other words, we are going to consider behavior of the system on the infinite time length from zero time, initial time zero, to infinity. In addition to this infinite horizon optimal control, we will also look at the finite time optimal control, because sometimes we don't want to consider infinite horizon, we want just to be optimal on the finite time horizon. And last but not least important, it's a model predictive control with linear models, which is nothing but essentially a linear quadratic regulator on the finite time, which is augmented or added with the constraints. Having this in mind, let us consider the following. We have a linear time invariant system, which is given with the following: x dot equal ax plus but, and as you can see, there are several different time evolutions of these states. This time evolution can go down, up. In all of these cases, we have a stabilizing control law, but all of these trajectories are essentially different. What is the difference? The difference is in an application of the control, which is ut is equal minus kxt, and we show that we can always find a case such that a minus bk is stabilizing. However, this k previously was never optimal, and this is the reason why we want now to consider the optimal setting. And what will be the optimal setting? In order to define the optimal setting, we always have to define some cost function, because optimality is always reflected with respect to some cost, defined cost. In this case, cost is going to be quadratic form of the state evolution of input evolution. We want to have a quadratic form because this is always positive and this is always positive. So even that u can be positive or negative, ut square is a positive. Even the x can go up and down, being positive and negative in the state evolution. This cost is going to be always positive. In addition, we can define the state vector here, which is not scalar quantity as the previous, but we can have a x transpose qxt, u transpose rut, where now q can be a positive semi-definite, while r is always positive definite. In other way, we assume observability assumption, which holds, and this prevents that x does not blow up. In other words, we want to ensure that R is a symmetric positive definite. Therefore, we have minimization or infinite time optimal control problem, and solution is to find the u of t, find the input if possible, by minimizing this cost. And cost again is a quadratic form with respect to evolution of the state and evolution of the input, subjected to the x dot equal ax plus but. Okay, let's prove that. Let's suppose that there exists a positive definite function such that x transpose pxt is some quadratic function here. So I'm saying x transpose t pxt, this is like something like a positive definite. And if we take derivative, we will have x dot transpose pxt plus x transpose pxt. This is very well understood. The next step is that we utilize, instead of x dot, we substitute instead of x dot, we substitute ax plus bu. We substitute, and now we have this expression. This is expression with all correct transposes. Okay. Now, if I integrate the expression to the left, this expression, I integrate from 0 to tf, dt, df, dt, this dt and dt cancels, and I have integration of the function that is dx transpose t p xt. But this is nothing but the evaluating integral between xtf and x0. So right side, we didn't touch this right side, we just copied here, but the left side is x transpose t final p xtf minus x transpose its initial quotient px at 0. Since tf is infinity and we assume that tf is at infinite time the state is stabilized, therefore it goes to 0, we therefore assume that this term in infinity is 0, right? Such that we just have minus x0 equal this. I take this term, deliberately flip on the other side, and I have that 0 is equal all of this, right? Now, previously defined cost, if I add 0 to the previously defined cost, nothing changes. Therefore, the overall cost is 0 plus previously defined cost, which becomes now the following expression. Okay, this is the following expression. If now this entire integral function is 0, right, we find for which u and which x this will be the smallest. Obviously, this will be the smallest when entire integral is equal 0. When this will happen? Let's add x transpose p transpose br minus 1 b transpose px and subtract from this equation and use r minus 1, and let's look what we have. Okay, we will have the following, that all these terms will group as a transpose p plus pa plus q minus p transpose br minus 1 b transpose p plus this term multiplies u transpose r minus 1 b transpose plus all of this, and this entire term dt plus 0. In other words, we rewrite this as follows. Term that has x transpose and x, term that has u and everything else. So I'm saying if this term and this term are 0, the only cost is x transpose 0 px. Therefore, by setting this first term to 0, we have that algebraic Riccati equation. If it's satisfied, we find the p. And by determining the matrix P solution to the full state feedback control by solving u transpose plus r minus b transpose px equals 0 makes the second term in this equation 0, such that these two terms are 0, so the remaining cost is this. Therefore, u of t, which is optimal, is minus r minus 1 b transpose pxt, which is now k, and k contains p, and p is solution of this Riccati equation. Therefore, only term that is left is this optimal cost of the initial condition. Okay, that's very nice. Let's now just see that optimal, infinite time optimal control solution is stabilizing. We apply input u that was previously calculated as a minus r minus 1 b transpose p xt, and we obtain now that a minus br minus 1 b transpose p is a new matrix, and the solution of this closed loop state matrix is as follows, where this is a stable evolutionary operator. Now the question is that, is the system stable, and can we prove the system is stable under this gain k? Let's suppose that q, r, k, and s are real positive matrices with r being positive definite. And here we claim that p a minus bk, because we know a minus bk is stabilizing control law, a minus bk, if k is stabilizing, then this is like some other a tilde, p a tilde plus a tilde transpose p is equal some negative definite. If a minus bk is stable, then p has to be positive definite. That's from the well-known Lyapunov equation. Therefore, we start from the Riccati equation. Let's write Riccati equation. This is q plus a transpose p plus pa minus p br minus 1 b transpose p. Okay? And after we define k as follows, we can essentially from this expression, nothing changes, Q plus A transpose P, Q plus A transpose P plus PA, minus PBK. We just, instead of all of this, we just put K, right? And now we group PA minus BK. Here we add K transpose B and we subtract, so nothing changes. When we factor this out, this becomes Q plus all of this P plus B A minus BK plus this, okay? Finally, PA minus BK plus A minus BK transpose P is equal negative definite. This term, R is always positive definite, K, everything is positive definite, Q is positive definite. So if A minus BK is stabilizing, again, P is positive definite. Finally, LQR infinite time optimal control places the eigenvalues of the closed loop system in the left half of the complex plane. Therefore, P must be a positive definite since it will satisfy Lyapunov equations. This is something that we learned already in the course. Also, if P is positive definite, then implies that this matrix must be stable. The optimal cost is always given in the terms of the initial condition, which implies that P must be positive definite and unique. Therefore, solution to the Riccati equation is unique since the minimum cost is unique, right? You cannot have this x0 and to have two different P, P1 and P2. No, it has to be unique P. Okay, so this is infinite. How about finite time? But finite time is just from T0 to Tf. Everything stays the same. Now we consider finite time horizon. We don't consider on the infinite time horizon. Setting is again identically, however, we have some function. Previously it was x transpose P, which was not function of t. Now we have a function of t. And this is a Lyapunov function. If we repeat the identical procedure again, and writing everything in the similar form, the only thing that is different is that we will have this contribution of the TF term at PTF and PTF, and we will have a derivative, P dot. In other words, we will have to solve time-varying Riccati equation, which is differential equation. P dot T plus Q and all of this is the same like in previous case. And we use the initial condition at PTF. In other words, we start with this side and we calculate P of t, because P of t is a function that has to be calculated from PTF to PT0. In other words, the solution to the full state feedback control is given by solving the following: P of t, x of t, and now we see that this is time varying again. K of t is time varying. Okay, all of this now, interestingly enough, has a additional discrete form where instead of continuous system I have a discrete system setting. Instead of integral, the objective again is to perform minimization of something that is summation. So we have again minimization of some cost, which is given as minimization of summation of some quadratic terms, which are again associated with the index. In other words, finite time optimal control again is going to be the following controller, and this following controller is going to give slightly different k in the case of the discrete system. And in this case, S is unique positive semi-definite symmetric solution of discrete Riccati equation. There is a slight difference in discrete setting with respect to the Riccati equation. Continuous Riccati equation and discrete Riccati equation are slightly different. There was P, here is S. We are calculating there for the continuous, for the P on the infinite horizon, here is S. Okay, now what is model predictive control? Model predictive control is nothing but discrete optimal control, which is augmented and it has constraints, and not only that, is applied in some repetitive manner. The main reference for this is Muschirone's 1993 paper, so it's pretty much around 20 years ago. And regulator formulation is again considered discrete state space setting. And at time k, the input is determined from minimization of the infinite horizon open loop quadratic objective function. This objective function now assumes the Q is symmetric positive definite matrix, the R is a symmetric positive definite penalty matrix, and now everything is in terms of vectors. In this sense, the vector U contains n future open loop control moves, and we are solving for the discrete U because now everything is discrete. And this is done in algorithmical fashion. Namely, the MPC receding horizon regulator solves for the finite time horizon, and once the solution is obtained, at time k plus n, the vector un is calculated from the open loop objective function. Then the only first input is injected into the plant, and this procedure repeated at each control interval with the feedback form from plant measurement, which update the state vector at time k. In other words, we have minimization of the following open loop quadratic function. We solve, we obtain the u, we apply, we repeat. Solve, apply, repeat. Solve, apply, repeat, and this repeats as we are marching during the time. So this is the end, and this is the short introduction in the model predictive control realization. For any questions, please feel free to send me email and I will be happy to provide answers.